Okay, guys, the next unit, 3C, is sketching polynomials. Let's hide this. I asked you to do this Desmos exercise on cubics. Just explore this. If you haven't do it, just go through this. It's very straightforward. So let's see. Next, classifying polynomials. We saw in the last unit a polynomial has the form ax to the n plus bx to the n minus 1, so forth, down to the constant. We are interested in this class in four equations functions: linear equations, quadratic functions, cubics, and quartics. The order we know: the linear has the highest exponent, it has 1. With the quadratic, the highest exponent is 2. Cubic is 3. Quartic is 4. And we're interested in we start off by looking at the shape of the curve, and we can look at the lead coefficient, the a, to tell us what it looks like. If it's positive, it's a is greater than 0. And if a is greater than 0, we have a linear that's increasing, a quadratic that's a smile, the cubic, and the quartic. And the idea is, if it's a positive polynomial, as x goes to infinity, the function or linear equation is increasing also to infinity. So we can see it's going to infinity, going to positive infinity, going to positive infinity, going to positive infinity. We don't know where it came from, but we do know where it's going. If a is less than 0, we have called it a negative polynomial, and we can see with the linear, it's decreasing. A quadratic is the smile. Cubic looks like this, and the quartic look like this. And the idea is, let me get my face out of here. The idea is that as x goes off to infinity, the functions the linear equation is decreasing. Whoops. Decreasing to negative infinity. Once again, we don't know where it came from, but we do know as x goes to infinity, the function is going the equation of the function is going off to negative infinity. The next thing we want to talk about is the multiplicity of roots. Now, we hope that we're able to fully factor our polynomials. That is, we can represent p of x as x minus the first root, x minus p2, x minus p3, ... whose zeros are p1, p2, 3. The idea is to find where it crosses the x-axis, we set our equation equal to 0. And once it's factored, we just set each of these factors equals to 0. And then we find the roots. Graphically, those are our x-intercepts. In Desmos exercise, investigating cubics, we saw that a 0 repeated 2 or 3 times. Roots that repeat m times, we say, have a multiplicity of m. A root with a multiplicity of 1 is represented by a curve simply intersecting the x-axis at the roots. So we see here we have a linear that crosses the x-axis 1 time. The parabola has 2 roots, but each of them only crosses once. And the cubic has 3 roots. They're distinct. They cross 3 different places. A root with a multiplicity of 2, or any even, is represented by a curve that is tangent to the x-axis at the root. So the form is p of x equals x minus p squared times other roots with other multiplicity, but let's just keep it at 1 multiplicity, the multiplicity of 1 for the others. So a parabola who has a repeated root is tangent at the curve. We see here we have a cubic with a double root, and we have a quartic with 2 double roots, right? We see that the parabola here touches the x-axis just tangent, so that's a double root. The cubic has 3 roots. There's 1 double root and 1 single, and this quartic has 4 roots. Or maybe it's a polynomial with an even power, but it's like a double root or a quadruple root. A root with a multiplicity of 3 or any odd is represented by a curve that also intersects the x-axis, but seems to flatten at the x-intercept. I hope you saw this with the Desmos exercise. And it's in the form p of x equals x minus p to the 3rd power times the other roots. Let's just focus on the triple roots. We saw this with the Desmos exercise, and then we see two more functions that seem to have triple roots. Let's see. Oh, whoops. Here we go. In the first one, we see this is a cubic, and it has a triple root right here at x equals 2. Over here, we have two triple roots, which means this is a polynomial of order 6, or, it's of a multiple of 6. This might be a polynomial of order 12. And then this one is we're assuming this is a quartic with a single root and a triple root. Whoops, let me see. Okay, so in this class, let's go on. Let's talk about complex roots for a second. We're going to be talking about that in a second with our quadratics, but not really with our higher orders. Polynomials with order 2 or greater, can I talk to you later? May have complex roots. In Algebra 2, you saw that parabolas with complex roots did not intersect the x-axis. For example, x squared plus 2x plus 5. We see the same thing with polynomials with cubics and quartics. Whenever the cube seems to approach the x-axis but then turns away, this indicates complex roots. So we see this quartic, and it doesn't really touch the x-axis, but there are roots. They're complex. Once again, we see the curve kind of like getting to the x-axis, but like kind of turns away. Same thing here with this cubic. We know there's a single root. That's real, but we know there's two more roots. Well, we see over here, it kind of like starts to approach the x-axis, but then like turns away. And the graphs of cubics and quartics with complex roots will not show up on the IB exam. You might be asked to find them, but like you're not going to be asked to analyze graphs. Once again, that may be an interesting exploration. So how do we sketch a curve based on an equation? Well, look at the equation. From the order and leading coefficient, determine the general shape of the curve. Second, find the y-intercept. Third, factor the polynomial to find the roots and determine their multiplicity. If you're asked to do this on an exam, the roots are going to be easy to break up. Maybe you'll be given a clue or something like that, but it's not going to be, that's a little old school. We'll talk about other ways to factor polynomials. Let's look at an example. I changed it from the book. So it asks you to sketch x equal x minus 1 times x minus 3 to the second power. So the first thing we're going to do is we're going to rewrite 1 minus x as negative x minus 1 so we can see it has a negative cubic. Second, let's see, next, the y-intercept is 9. So find the y-intercept, x equals 0. 1 minus 0 is 1, 0 minus 3 is negative 3, square is 9, the y-intercept is 9. And then you're going to find the roots. Well, it's already factored for you, so you already know that x equals 1 has a multiplicity of 1, and x equals 3 is a double root, a multiplicity of 2. And so you can see that's represented in your graph. So you've sketched it. It's not perfect. Maybe you didn't even use a piece of graph paper, but you kind of let the viewer know this is what the curve looks like. This is the y-intercept. These are the roots, and this is how the curve behaves around the roots. Remember, you can, Remember, you can verify all of this with your GDC, Desmos, or GeoGebra. Next, here's a question from the book. Find a possible equation for this graph. So immediately you look at it, and once again, you're asked to work backwards. So I want you to think about, what do you see? What do you notice about the shape of the curve? And what do you know about the roots? And what about each of the roots? Okay, let me move my face out of the way. Okay. From the graph, we can see that we have a positive quartic. We see that two roots, 2 and 3, have a multiplicity of 1, while there's a double root at negative 1. In addition, we see that the curve passes through 124. So we get all this information down. You get points from IB from just writing all this info down. We can create a partial polynomial, p of x equals a times x minus 2 times x minus 3 times x plus 1 squared. I have to put the a in there because I can write like an infinity of w's that like pass through the 1 at a that touch -1 and pass through 2, 3. But there's only one that passes through 124. So solving for a, we know that p of 1 equals 24. Substitute the 1 into the polynomial. We get a times 1 minus 2 times 1 minus 3 times 1 plus 1 squared. That equals 8a. Therefore, a is 3. That's what IB wants to say. They just want to see the work. We're done. 3C, all of it.